SwayamPrabha. Digital India. Educated India.
Welcome to the second lecture of week 6. Today we will discuss about deriving the constitutive relations of a composite ply with the help of rule of mixture based homogenization. So, we will use rule of homogenization for constitutive relation of composite ply. Using rule of mixture. Now, if you want to do it, we have to make some assumptions. So, there are some assumptions. These assumptions are both fiber matrix are homogeneous and fiber matrix show linear elastic behavior, and then we also assume that there is perfect bond between fiber matrix and ply, which we will also call lamina, does not have residual stress. Now, and we also assume that fibers are regularly spaced and perfectly aligned. And also they are uniform. Now, with these assumptions that make the situation somewhat ideal, we will derive all the relations. So, our ply have both matrix and laminate. So, if we assume that Vf is the volume, our ply have both matrix and fiber, and if we assume that Vf is the volume of fiber and Vm is the volume of matrix, yes, and then we say that Vc is Vf plus Vm, which is the total volume of a ply. Then we can define something like Vb by Vc, which we call capital VF, which means this is fiber volume fraction. And then similarly we can write Vm by Vc, which we call Vm is matrix volume fraction. And if we add Vm plus Vf, this is Vf plus Vm by Vc, and we know that Vc is also Vf plus Vm, so it is 1. Now it is assumed that there is no void. If there is any void, so accordingly there can be a void volume fraction also, and then void volume fraction plus volume fraction of matrix and fiber, that becomes 1. Similarly, we can define weight Wc as Wm plus Wf, where this is Wc is weight of ply and this is matrix weight and this is fiber weight, and then using the same logic we can write the matrix weight fraction plus fiber weight fraction is 1. This is matrix weight fraction, which is weight of matrix by weight of composite, and this is fiber weight fraction, which is weight of fiber by weight of composite. Now we can write that rho f into Vf, where rho f is the fiber density of fiber plus rho m into Vm, which is density of matrix. We can write this as rho c into Vc. Here rho c is density of ply, and again this can be written as rho f Vf plus rho m Vm is equal to rho c. So the density of the ply is weighted combination of the density of matrix and density of fiber, where the weights are the volume fractions. We can also write weight of composite by the density of composite, which is the volume of the composite, as weight of the matrix divided by the density of the matrix, which is the volume of the matrix, plus weight of the fiber, density of the fiber, which is volume of the fiber. So from here we can write, we can directly show that the density of fiber can be written as weight fraction of fiber divided by fiber density plus weight fraction of the matrix divided by matrix density. Now if we have something called void volume fraction, as Vc. So this is volume of void. So if there is void, then the density thus calculated is going to be more than the actual density. because here we do not have any void, and voids do not have weight. So, this is, we know the density that is got theoretically, and experimentally if we get any less density, then it becomes rho Ct, which means theoretically obtained density, which is this, minus rho Ce, which is experimentally obtained density, divided by rho Ct. Now, we will define the elastic properties. So, let us talk about longitudinal elastic modulus. So, our composite ply looks like this. We have plies oriented in some direction, some theta, its plies are oriented and there our assumption is that they are aligned properly and spacing is uniform. So, here we can talk about two axes, one is let us define as x and y. So, this is we can say it is a global axis, and we can align another axis we can define another axis which we assume to be oriented along the fiber direction, and let us call it axis 1 and let us call it axis 2. Now, 1 2 is principal material direction, or we call it principal axis. Now, we will find out the properties of the plies in the principal axis. So, along the principal axis we can make the same drawing as this. If we draw it along principal axis, it will look like this. Now, our goal is to find out the elastic modulus along direction 1. So, let us idealize and assume that all the fiber volume is concentrated on one side and the matrix is at the other side. This is just an assumption, idealization I would say, for the sake of illustration. It has nothing to do with the physical picture, it is just for the sake of illustration. We are showing that fiber is at the other one side and matrix is at the other side. And let us assume that this entire lamina in the direction 1 is under a stress sigma 1. So, sigma 1 is applied along direction 1, and then under the action of this deforms, and it deforms in this way. The deformed shape can look like this. The red dashed line shows the deformed shape. So, what is happening here is, because there is a perfect bond between matrix and fiber, so one is not going to slip over other. So, they are always in contact, which means that the longitudinal strain experienced by the fiber and matrix are same. So, strains are same. So, the total load carried out by the matrix and total load carried out by the fiber on being added would give me the total load carried by the ply. And so, we can write sigma 1 f which means the sigma 1 in the fiber is equal to multiplied by the area of the fiber plus the area of this face, I am the area normal to the one axis, plus sigma m multiplied by area of the matrix is equal to sigma 1 multiplied by the total area of the matrix and fiber. So, here sigma 1 f means the stress at the fiber, sigma m means stress at the matrix, and sigma 1 means the sigma 1 over the composite. Now, stress are not different, whatever the stress here, whatever the stress here, and they are just sigma 1. So, sigma 1 is equal to sigma f is equal to sigma m. Now, sigma 1 f is ভুল হয়েছে। Now, sigma 1 f is E 1 f multiplied by epsilon 1 and we are multiplying that with A f. F sigma m means E m and that is multiplied with epsilon 1 and we are multiplying that with A m, and then we have sigma 1 which is E 1. E 1 is equivalent elastic modulus of the ply, that is multiplied with epsilon 1 into A m plus A f. So, please understand the stress are different, but the strains are same. Then E 1 cancels from both sides and we bring A m by A f in the denominator here, and that gives us E 1 f is equal to V f plus E m is equal multiplied by E 1 f multiplied by V m plus E m multiplied by E 1 f multiplied by V f plus E m multiplied by V m is equal to E 1. Because if we have A f divided by A m plus A f, it is the ratio of the fiber area divided by the total area and the other dimension is same. So, it is the ratio of the volumes also and that is V f. Similarly, A m by A m plus A f is equal to V m. So, that is our elastic modulus of the in the longitudinal direction of the composite in terms of the individual elastic modulus in the longitudinal direction of the matrix and fiber. Now, given this figure, if we now given this expression, if we want to see the variation of E 1 with change in E f, it would look something like this. So, this is our V f, it is increasing in this direction, this is V f equal to 1. So, when V f equal to 0, which means there is no fiber, E 1 is just equal to E m, and when V f is equal to 1, which means there is no matrix, it is only fiber, then E1 is equal to EF, and in between them they are varying linearly. And also if we look at the individual stress strain behavior of the matrix and fiber, it looks like this. The fiber behaves like this. So, the fiber does not break suddenly, and then we have the it is the matrix. So, the matrix behaves like this, the matrix does not break suddenly, and then we have the fiber. Fiber has a much higher elastic modulus and it is brittle, it breaks all of a sudden. And the composite is somewhere in between. So, the elastic modulus of the composite along one direction is between what we get for the fiber and for the matrix. So, fiber is very stiff, matrix is relatively less stiff, and the composite is in between. So, it is E1F, this is EM, and this is E1. Now, we will talk about the same properties in the transverse direction. In the transverse direction, so we look at the same idealized diagram. When it is loaded in the transverse direction, we have fiber here, we have matrix here, it is loaded in sigma 2 direction, stress is sigma 2, this is direction 1, this is direction 2. Now, after deformation, this can look like this. So, there is delta m, which is displacement, I mean the elongation of the fiber which matrix, and then there is delta f, and combining delta m and combining delta f we can. So, there is this is delta m plus delta f. Now, combining delta m and delta f, we get the total deformation. Now, here the stress is same and strain is different. So, the total delta, which is delta m plus delta f. Now, delta m is the elongation in the matrix part in the transverse direction, which can be written as strain in the matrix multiplied by the length initial width. So, if we did say Bm is the dimension of the matrix part along 2 direction, and Bf if we say matrix of the dimension of the matrix along the 2 direction. So, it is epsilon m multiplied by Bm, it is epsilon f multiplied by Bf, and then we have delta is equal to epsilon 2. So, we can call it epsilon 2f. So, epsilon 2 multiplied by the Bm plus Bf. Now, epsilon 2 can be written as sigma 2 divided by E2. Sigma 2 is the stress along the second direction 2. E2 is the equivalent elastic modulus along direction 2. So, Bm plus Bf, epsilon 2m is again the stress along direction 2, which is same. So, epsilon 2 by Em, and then we have Bm, and then epsilon 2 divided by E2f multiplied by Bf. Now, epsilon 2 is same everywhere. So, it cancels out. We have 1 by E2 is equal to Vm by Em plus Vf by E2f. So, this is our relation for the elastic modulus along direction 2 in terms of the elastic modulus of the fiber along direction 2 and matrix elastic modulus. Now, Em is generally used as Em prime, where Em prime is Em by 1 minus nu m square, and it is for the incorporation of due to fiber in the fiber direction of the matrix. So, to incorporate the constraint due to the fiber in the fiber direction of the matrix, Em is often modified to be Em prime and used in the formula. So, this is what we get when we use this kind of strength of material based approach using rule of mixture to get the relation. Now, Halpin and Shai they proposed a formula E2 is equal to Em multiplied by 1 plus xi 1 eta 1 Vf by 1 minus eta 1 into Vf, where eta 1 is equal to E2f minus Em divided by E2f plus xi 1 plus Em. So, xi 1 is called reinforcing efficiency, which is generally xi 1 ranges from 1 to 2. So, through experiment we can try to fit the formula and find out what is our xi 1, and then whatever the xi 1 is used, we can use the same xi 1 for this material, for this ply material. Now, if we look at the variation of the transverse elastic modulus of the ply with Vf, the plot would look like this. So, here the variation is not linear. Again the same thing, this is Vf equal to 1. So, when Vf equal to 1, the entire ply has only fiber. So, elastic modulus is just Ef, E2f, and when Vf equal to only matrix, the elastic modulus is just Em. Now, we will find out the in plane shear modulus. Now, to find out in plane shear modulus, again let us assume our ply is loaded in shear. So, we have shear tau 1 2 and we have the matrix part here, sorry, the fiber part here and the matrix part here. Now, due to this kind of shear, the deformation would look like this. Now, this is delta m plus delta f due to shear, and this is our delta m, and this extra portion is delta f, and that is the result of shear. And also we have this as our dimension of the fiber part along the second direction. This is the dimension of the matrix part along second direction. This is direction 1, this is direction 2. So, again we can write that delta is equal to delta m plus delta f. Now, this delta m is nothing but the shear strain in the matrix part multiplied by this dimension Bf. Similarly, delta f is the shear strain in the fiber part multiplied by the dimension of this dimension Bf. So, delta m is shear strain in the matrix, which we can write as gamma 1 to m and then that is multiplied with Bm. Similarly, this is gamma 1 to f and this is multiplied with Bf, and delta is the equivalent shear. If I just join this point to this point, the line that I get that shows some angle here, and that is going to give me, so this angle is our equivalent shear gamma 1 2 and that multiplied by Bm plus Bf. Now, equivalent shear gamma 1 2 can be written as the applied tau 1 2 divided by equivalent shear modulus G 1 2, and then we have Bm plus Bf, and gamma 1 2 is again tau 1 2 that is applied. So, stress is same throughout and that is divided by Gm multiplied by Bm, then we have tau 1 2 by G 1 to f multiplied by Bf, and finally, after cancelling out tau 1 2 and bringing Bm plus Bf in the denominator here, we write Vm by Gm plus Vf by G 1 to f, and again the relation would also look same as that we saw for the transverse modulus case. So, if we plot Vf here and if we plot G 1 2 here, the relation would look like this. So, here we have Gm, in this side we have G 1 to f, and this is Vf equal to 1, this is 0. Now, there is a equation by Halpin and Tsai for this case also. And as per that equation, it is Gm multiplied by Gm multiplied by, in the denominator, 1 plus xi 2 eta 2 Vf, then divided by 1 minus eta 2 Vf, where eta 2 is G1 to F minus Gm divided by G1 to F plus xi 2 Gm. So, again we can experimentally find out xi 2 and we can fit the equation and we can use the same equation. Now, this brings us to the end of this lecture. We will continue from here in the next lecture. Thank you.